Okay, I think it's time to start again. Right, so welcome back. It's going to be another lecture, and we're going to start off from where we stopped yesterday, I guess. So yesterday we had to kind of rush through the whole CMake experience because there was not really enough time, because we spent some more time on like debugging and showing the internals than I expected. So today we are going to talk about using unit testing for your yeah, sure. The audio on this recording will not be the best. Right, so today we're going to be talking about how to use unit testing for your code, what are namespaces, which we already have seen, but now we will understand how to use them and what they are. And we will start the introduction to classes, which will be a huge part of this course, really. And before we start off, I think I will go through the whole CMake thing again, but I will not show you slides. We will try to code something, right? So to give you a perception of how hard is it to set up a new project in CMake, for instance, right? So what I have here is I have a temporary folder, and I just created a CMake project folder, and you can see that it's empty. There is nothing there yet. So what we will do is we will create an empty Cmakelists.txt. We will create a folder source. And for now, I think that's all that we need here. So for now, we have a Cmakelists and source. So let's go ahead and try to modify the Cmakelists. Okay, that is not what I want. Just a sec. Let me just make it more usable. Come on. Okay. Right. So let's modify the Cmakelist. And as I told you, there are two commands that you must call. It's project, and let's call it CMake test project. And we need to specify the minimum version that we ask from our system to have, and of CMake. And we're going to be working with version 3.0. So it's not very important which version we pick. Just don't pick. So anything that starts with 3 is fine. Now I think CMake is on version 4.5 or something, but 3.0 is a good start. The timing. Okay. So this is kind of the bare bones project that we can set up. And to build this project, I think we can already build it at this point, even though it doesn't make any sense. But building, you can do it from the same folder, but then you have a lot of files populating your project, which is a pain to clean up. So never do it not in a build folder. So you always want to create a build folder, and it's an empty folder, so there is nothing there. And what you want to do is you want to do CMake ... So CMake takes a folder, as an input it takes a folder with that contains a Cmakelists.txt, right? So our folder that contains Cmake.txt is one folder up from us, is our parent folder, so that's what we do. And so we run CMake, and it does a bunch of things. And at this point, it's not very important what exactly it does, but you can, if you look at it, you will see that it detects like the C compiler, it detects the C++ compiler, and it checks if your C++ actually works, and so on. So what it does is it populates this folder with a bunch of files over there. So a very Yeah, so basically the main file, the most important file over here is this make file. So the make file is actually, it's a sequence of commands that will actually be carried out, it's a sequence of commands passed to compiler. So this thing actually calls the compiler. And you can look up what this file looks like. It's usually kind of scary because CMake generates a big one. Let's see if we find anything useful in here. Not really, because we don't have any code yet. So there is nothing that is useful here for now. There will be. And the important part that you need to remember is you never need to modify this make file. This make file is only there to help you build the code, and CMake takes all the responsibility for it. So CMake generates it, and to run this make file, you just need to run make. And in this situation, it doesn't do anything because we don't have anything to build. We didn't add any files to our project. It's a dummy project for now. So let's add some files. Again, like if at any point something of what I'm doing is not clear, stop me, ask me, because you need to understand this very well, because you will use that for homework. You will need to set up most of the CMake project on your own. Right, so let's modify our CMake lists. We did have a folder source there, so that's where all our sources will go, and we will populate it at some point. But for now, let's just try to use that folder even though it's empty. So what we want to do is we want to add subdirectory, and we can either just say source here. So again, in CMake, everything is string. So by default, this source over here will be a string. Let's probably even make it a bit bigger. Okay. And also all the relative paths will be extended from this CMake lists file. So from the folder where the CMake lists lives. So in this situation, we don't specify any path over here, and usually it will be extended from the root of our project, because that's where our CMake lists lies. If you want to be really precise, if you want to know exactly what is going on, you can use variables. So you can use project source dir, whoops, and add a slash to it. This way, you've just constructed a path, like a full path. So this variable over here, it's a CMake variable, it's a standard variable, it's going to be populated on every run of CMake. And this variable will be so you will concatenate this source to this variable over there, which will give you the path to your source folder. We can also, to make sure that everything works, we can also output this project source dir, and so let's have it so that we can easily see it. Let's just put some tag over here and copy this thing over. All right, so at this point, let's try to build it again. I wonder, no, okay. So just run CMake, and so first of all, we see our tag over here, and you can see that it has been populated to the folder where we actually are. So to where am I? To temporary CMake project, which is the folder where I created the project in. But then we also have an error, and this error is very descriptive. It's an error with this add subdirectory, and the problem is that this subdirectory doesn't have a CMake list at all, and it must have. Whatever you use with add subdirectory, there must be a CMake lists in it. It's a rule of CMake, basically. So let's make CMake happy, and let's go to source. And in the source, let's create a CMake list txt. So the cool part about CMake is you can specify your build hierarchically, right? So you don't need to specify all the build in one huge file. You can actually think in modules, so think modular design. So if I have my source folder and this source folder has many other folders, I can have a small CMake list for every of those, and CMake will handle that properly. But we can also have an example for that if needed. So let's just save this empty file. There, it does nothing. It just exists there, right? And let's try to rebuild our code again. Okay, so now it builds. It still shows us our message. And everything is fine because now it found the CMake list, but it's an empty CMake list, so it doesn't have to do anything, but at least it has found something. So if we type make, it still does nothing because the make file that it generated does nothing. It just sets up the project, and that's it. Okay, at this point, let's probably add something useful to it, right? Or at least borderline useful. Let's, in the source folder, let's add some files like, so let's add for now one file, say main CPP, and it's going to be our typical, nope. So it's going to be a main function, and yeah, let's do something useful. So let's do, again, like the hello world application. I think it's fine to do here. So, yeah, hello is enough. std and del. All right. So now we have some file over here, and we can build it on our own. We have done it many times, so I will skip it here. But we now also need to tell CMake that there is such a file, that it has to build this file. And for that, we need to modify the CMake lists within the source folder, so the one that is in the same folder with our file. So we go here, and there is a very simple command. It's called add executable, and we just say we want it to be called main, or let's give it some other name to make sure that there is no ambiguities and you understand exactly what goes where. And what we want to specify for it is we want to specify that all the files that should come into that executable. Usually it's one CPP file. You generally want your executable to contain one CPP file with one main function, right? So whenever you do add executable, that is a thing that you will be able to actually execute. It will be a binary, and it has to have a main function in it. Okay, so at this point, we have done something useful with the project, so let's try to do it again. So we did the CMake. It showed us exactly the same things as before, but now if we type make, there is something happening over there. So you see all this colorful output, and the percentage of how far are we in our build. And basically what it does, it creates all the boilerplate things that we did before, like create objects, link objects, and so on. It does them here, and you can just use your bin main. So let's see what we have in our build folder now. Again, all the build files will always be in the build folder. They will not be scattered around. And this is a pleasant feature, because the build folder you can just ignore from your Git, and nobody should ever see it apart from you. So it's your local folder, and if you are not happy with your build, you just remove it and start over again, right? So now it has a new thing there. Before, there was no source folder over here. Now there is source folder over here, and if we go to this source folder, there is some more files that are needed for CMake, but there is this binary over here. So if we just run it, it's going to print us hello, so just to show that it actually works and does what we expect it to. Right. So why is it stored in source folder? That's because the actual file is in the source folder. So the structure of the build folder mimics the structure of your project. If you have something in source blah blah, it will be in build source blah blah. Okay? Good. But then why do we need CMake at all is not for just creating executables. We know how to do that. That's really simple, right? So we want some library. let's try to add some library to the project. We need to go back to the source folder, and let's create some, no, not make dir. Let's do some header file. So let's have a hello.h, for instance, because that's what it's going to be doing. Again, the name of the file kind of should represent what it is supposed to do. Okay, so if we go to hello.h, we first need to start with pragma once, because we don't want it to be included multiple times. Again, including means copying. So if you don't do that and you have multiple includes in your whole project, and this file gets included multiple times, it means that it will be, so you will have the definition of the function, exactly the same definition multiple times in a row, and that will be an error in your compiler. So if you forget that, you will get errors while compiling your code. Okay, and let's have some function. It's going to be a void function. It's going to be print hello. And what we want to do is we want to also add iostream here. And we want to print the hello function here. All right. So now we have our extremely useful function, and you can see that I now not only declare it in header, but I also define it in header, right? So that's a bit different from what I was talking about, and I feel like it's important to understand the differences. Now, what can I do about it? Let's go to the main function, and let's remove our cout. We can now include the other file, and we can include it with just typing hello.h. This is something that Google tests will actually not be happy about, because it will tell you that you need to include the directory when naming a .h file. And I hope, okay, that is seen, good. And we will come to that later. If you just wanted to shut up, you can do something like this. This means that you're looking for something within this folder, but you're explicitly specifying a folder for it. This way, you don't have a warning, but it's not a very proper way of doing it. We will come to that probably later. Okay, so at this point, we use our hello, so now we can actually use the function. So let's try to use our function, and we use the print hello function over here. So do we need to change anything in our build? Like, who has some understanding of what is going on? Like, who thinks we need to change anything in our build to build it? Okay, do you have a guess of what?
Maybe like we have to update the .h file.
What do you mean update?
Maybe I'm on track, but have we already saved the header file with the content, and then also saved the main file?
Yeah, we did. Okay, yeah. So anyway, like, you don't need to modify your build at this point at all, because header files are just copied, right? So you basically just have, if you just include it, you don't need to link anything, you don't have to do anything. That's called, so what we now have implemented is a well-known word of a header-only library. So it's a library that consists only of headers, everything is implemented in headers, and you never need to link it. That's the good part of it. But it needs to be compiled every time it's included. So every time you include it, it's not for free. You need to pay with your compilation time for it. So in this situation, we can go to our build folder again, and we can rerun cmake, run make, and let's do our source bin main. And now we get an output hello function instead of hello, right? So it uses our function. We didn't need to do anything. We didn't need to modify the build. CMake doesn't have to know about header files apart from where to search for them. And there is a difference between using the brackets, kind of the angular brackets like this, and the quotes for includes. The difference is that if you use the quotes, the compiler will think it's a local file. So it should be searchable from within this file over here, the one that we are in, right? So in this situation, we have a so in the, actually, let's even do it here. Oh, no. Okay. Maybe I can. I just want to show you the structure of the project. And yeah, so the main, okay, that was not a good idea because we have a build. So let's remove the build. Okay. So our structure of the project looks like this now. So we are here, and there is a source folder, there is a hello, there is a main CPP, and you can see that hello is in the same folder as main CPP. So that's why we are able to find it with the quotes. I believe that if we put not the quotes but these symbols over here, we should get an error. I hope. Otherwise, I'm wrong. CMake. Yeah, okay. So you can see that now it cannot find the hello.h file. That is because if you use the angular brackets, it does not search for this file within the same folder where you are. So it doesn't consider it to be a local path, but it considers to search it in all the system paths that it has. And these are a lot. We will not go deep into that now, but there are many system paths. And what you can do, and what you usually do, you don't usually search for headers in your local folder, but you usually specify in the CMake a folder where all your headers should be found. So let's try to do that. Let's help CMake finding this file. For that, we need to modify the topmost CMake, the one that has our status message. And for that, we need a command that is called include directories. So include directories tells CMake to specify whatever folders. It can be many folders here. It doesn't have to be one. It can be as many as you want. And the list just looks kind of like this. So if you want more of them, you just add more of them. It's very easy. So what it tells us is that all our headers should be searched for starting from that folder over there, in addition to all the other system folders that are already there. So what it tells us now is that we expect that our headers should be in the source folder. So now that we added this, let's try to rebuild our project. And now it suddenly builds, because now CMake can find those files. Okay? Are we on the same page? So everybody understands the difference between the angular brackets and the quotes, right? Okay, good. Right, so for now we have done a header file, but we didn't really do a library. We still could have just done the same thing with our common C++ way of just compiling it all in the command line. It would still all work. We don't need any linking there. Where CMake shines is where you have a lot of things that should be linked together. So let's try to do that. Let us modify our, so let's create a new file. Let's go to source, and let's create a new file, hello.cpp. And we will just copy this function over there. And this file needs to, so every CPP file that is part of a library should include the file with the headers of this library. So every library has headers, which is the definition, and the implementation, which is the CPP, right? So they should be separated, and they usually have the same file name with the only difference of one is being .h, the other is .cpp, okay? So what we need to do is we need to include here hello. And we know that hello is in the same folder, so we can just use the quotes over here. And what it now says is, like, I mean, I could compile it, but it does the same thing for me. It just shows that there is a redefinition of print hello. And why is that? Because there is a definition in the header file, right? So in the header file, we already had a definition of this thing. And we just need to remove that definition now. It has to just be a declaration. So why do people do that? What's the use of it? Like, why to complicate our lives separating things into multiple files? That's because it's much easier when you read the code. So when I read the code, I generally don't care about the implementation. Again, if the function is named in a proper way and everything is, and I trust the developer to some degree. I mean, you never trust somebody really, but they can convince you that they are trustable by providing, say, a complete set of unit tests for their code. And if I see that their library passes 100 unit tests and the name suggests that this function does it, I have no reasons to believe that it doesn't do it. So this way, I never ever need to see the implementation of the code, even if I can. What I need to see is I need to see the interface of the code, the interface by which I can call some code. And this interface is then encapsulated in a header file, and it's very simple to read. You just open it, you see all the functions, all the definitions of the declarations of the functions, and that is the only thing that you care about. So it does not contain any information that you don't care about. You don't have to scroll through it. You just look at the function, you look at its signature, you're like, okay, I can use this function like that. So that's why people do it, like one of the reasons. Good. So now we did that, and let's try to, so if we just try to build this thing now, we're going to get an error. We're going to get an error because there is an undefined reference over here, undefined reference to print hello. That's because now we only include the file, but CMake and our build progress doesn't know anything about the hello.cpp. We have never told it that there exists a hello.cpp. So the only thing it does is it just includes the header file, which just contains the declaration of a function, and we're missing a definition. Whenever we're missing a definition, we will get the undefined reference error. All right? So let's try to provide some help again to CMake with it. For that, we need to modify our CMake that is in the source folder. So we have an executable over there, and what we need to do is add library. So we want add library, and we want our library to be called hello, and the hello library is defined in the hello.cpp, right? So again, in CMake, you generally don't ever care about headers. Headers come for free. You can just use them, and that's fine. So you never need to define them. What you care about is the actual CPP files. So what this thing will do, it will find the hello.cpp. It will consider it like, okay, well, there is a CPP file, and I need to compile it. So it will compile this file into object files, and will pack them into a library for you. You never need to do anything about it. You will just get a library. And by default, you will, yeah? Okay, so let's try to open them side by side. Oops, I meant this. Oh, come on. All right, so on the left is the header file. On the right is a CPP file for the library.
So on the right, there's the code, like functions and so on, and that's
just the declaration of this function, yes. So this thing is called a declaration of a function. Like, it can be confusing. I always confuse these two words. the declaration and definition, they sound very similar, but basically declaration means you declare that something exists somewhere. You just say, well, trust me, it exists somewhere. That's what the header file is for. So the header file just generally tells you, like, here, use it like this, and trust me, it exists somewhere. The CPP file says, yeah, I'm the one who you trust. Like, I'm the one who implements the thing. And that's how you think about them. So every library has a bunch of header files and has a bunch of CPP files. And every header file tells that this is the interface to my library. Use it like this. The CPP file is actually doing the work for you. Okay? Good. Where did we stop now? So, okay, right. So we added a library. But the issue for now is that we now have a library, which is one binary object, and we have an executable, which is another binary object. But they do not know about existence of each other. And that is a problem, because from perspective of our bin main, it still has no idea where to search for the CPP file or for any object or for any compiled code that it can actually run, because it just sees the header. We still did not communicate the existence of the library to the executable. And that is what we do with the target link libraries. And we need to specify what we link. And then, okay, so the terminology here is kind of weird. So let me just first type it, and then maybe it's clear. So the first parameter is the binary that we want to link something to, and the second parameter is the thing that we are linking to it. So in this case, we say that our bin main should be, I'm not sure about the terminology, but anyway, consider them that they are now linked, okay? So now bin main, or whoever is on the first position of that function, knows about the existence of a library called hello, okay? Good. So at this point, this thing should work. And it compiles properly, so there are no issues in that. And you can even see that these lines show you what is being compiled. So it's scanning some dependencies of target hello. So there is a target, like everything that it compiles, it calls a target. That's how CMake likes to call things. And hello is our library, and you can see that it's linking a CXX static library libhello.a. So it has created a library. It's by default, it is a static library, and it created a libhello.a over there. Then it does the same thing for our binary. So in the binary, it does linking executable bin main, and it links the executable, and it also links it to our library. And at this point, we can just let it run, and we still get our hello function, so that thing works as expected. That is basically a very bare bones project in CMake done from scratch, right? So that's the minimum code that you need to make something run. But the cool part about it is now, if you have multiple libraries, you can use them all in the same bin main. So let's try to do that maybe. So let's go to source, and let's do a subl. What do we want? Any good idea for the function? I love this, yeah, blah. So let's do blah, and let's do blah CPP. So blah.h will be, we need pragma once, we need void print blah, include iostream. Wait, I didn't. So it should be just the declaration, and in the blah.cpp we need to include our blah.h, and then actually create our function over there. All right. So now we have two of them, and what we can do is we just need to modify the Cmakelists in the source folder, and let's now add another library, and let's call it, of course, blah. And now what we can do here is we can actually link both of them to our binary. So at this point, if we now also change our main function to also, it also has to include the blah thing, and let's also print blah. Good. So let's try to build this one. And this thing works as expected. Let's also run it. And it shows us the hello function and blah. Okay, so that's like, now we can add as many libraries as we want. We can link them to as many binaries as we want, and so on. So that's why people use CMake, because now it became very simple and very readable. So the good part is that this is much more readable than creating multiple object files, then putting them into a library, and so on. You can also specify which library will be created. So by default, it's static, and it's as if I would type static here. But I can also write dynamic over here. And let's try to rebuild the code again. There was an error. Why was there an error? Did I? Shared. Sorry, not dynamic. Sorry for that. It should be shared. All right. So the only difference, like everything still works as expected. The only difference is now we have .so in the end. So .a is a static library. .so is a dynamic library. And again, the way to think about that is a static library, when you link it into your binary, it just gets kind of physically copied into your binary. So whenever you move your binary around, the library will be inside of this binary. Okay? So your binary will get bigger, but it will have everything with it. So it kind of brings its home with it, you know, like a turtle or something. But if you have a SO library, it's stored somewhere else. It's stored somewhere on your file system. And the only thing that is added to your binary is a way to search for it. So when you run your binary, the first thing the binary will do, it will try to search for all the libraries that it needs to. And it has some predefined ways for that. We will not go deep into that, but it searches for one, and that's it. So that's all you need to remember about those. So if you want to distribute your library, you generally want to distribute it as a shared library. That is probably why it's called shared too. And if you want to keep your library and you want your code to run fast, as a rule of thumb, you generally have a static library. Good. So do you have any questions to that? Because now we can still try things out on a simple example. If not, we're just going further and deeper into that. Okay, who completely understands what is going on? Okay, whoever doesn't, what are your issues? What is not clear?
I guess it's just, these are just very many files.
Yeah.
Very much linking.
So
basically, we learned that in Java, we just, in Eclipse, you just click project, and that's basically what it does. And you have
yes.
folder, library lib folder. And I feel like this is pretty complicated for just using functions.
So I have a, like, my feeling about this is I totally understand what you're talking about. And the issue with simplicity of things is when they break. So whenever, like, I've also started my life as a C++ programmer through an IDE. So I used an IDE to do stuff, and I was just clicking one button that should magically do something. But then when something didn't work, I had no idea what to do. I was just randomly clicking stuff and like putting, like, does this, like, if I change this settings, then I Google for something and I'm like, oh, okay, well, does it change something? Like, if I put this here, does it change anything? And so on. Like, it's a painful process. And the problem, like the underlying problem of this whole thing is that you don't understand what you're doing. And I feel like, you know, you can use different languages. Like, so I have issues with using Java or Python as a, say, first language because they make things simple, but when something breaks, you instantly have to learn everything about it. And they are complex. Like, the underlying things behind that are really complex. This is kind of a middle ground. So yes, it is a bit more complex when you start with it, and there is, I mean, it's not too many files. It's like you have a project structure. It's, you have basically now 2 Cmakelists. They are completely hierarchical. So if you think about that as a hierarchical model, it becomes simpler. And everything that you need to actually compile stuff is within one Cmakelist, within one file, right, at this point. And what is good about it is that you can understand everything about it. You can understand every single step. Like, it's not that hard. And I understand every single step of that, and it means that I can teach you. So if you have any issues with that, you can ask me and I will explain exactly what happens at every single step, which means that it cannot backfire. It means that if you know what you're doing, you cannot like get caught off guard with something not working and you don't, and without understanding why, and just randomly clicking things. So don't randomly click things. If you don't understand something, ask me. Like, drop me an email, come to me, because this is like the cornerstone. If you understand this, everything will become much easier. Especially, like, everybody uses CMake in the world. Like, there are some companies that use their own system, but there are so many companies that use CMake and so many projects that use CMake, so you should use that. But yeah, I do get the point that from the start it can be a bit hard. So I hope you got here an intuition. You don't have to be able to write your own project from scratch by hand in CMake. So the only things you need to understand is that it's hierarchical, it runs line for line, and you need to understand what every of those lines does, at least on an intuitional level. And it will come to you a bit later of why this whole thing makes sense, I guess. It's just practice. Okay, I hope that you got the intuition here. Let's probably continue on. You will have a bunch of practice in the homework, so that's good. Right. So I wanted to start with CMake, with simple CMake, because we're now going to go into the more harder CMake. And the start of it is that I want everybody to write unit tests. Like, it's my mantra. Like, I make everybody in the lab do that. Like, in the companies that I work, they're always writing unit tests, and that is the thing that makes people trust your code. So if you don't know what a unit test is, it's fine. We will talk about it right now. But we will start to kind of the rationale behind this. Why should you even consider it at all? So we will use Google Test. So it's a Google testing framework. They used it internally for many years. Then they open sourced it on GitHub. And I think, so there was a survey recently, and 50% of everybody who uses unit tests use this system. All the others are have a much lower percentage. It's a very mature system, so you shouldn't expect any bugs in it. If you feel like something is not working in this library, it's probably in your code. So the idea of unit testing is that you want to catch bugs as early as possible. You don't want to catch them in a big system. You want to catch them in a really small controlled environment. So if you write your class, you want to check that every small function does exactly what you're expecting it to do. Because if you don't check that, and you include that class into some bigger structure of many classes, and it does something wrong, then to catch what went wrong, what was the cornerstone of your big error, is really hard. You have to dig deep into your code and find, okay, if I run this, if I run that, this value looks wrong, but is it wrong, and so on. If you have unit tests, you know that simple things work, and this is a very important basis for your code. I suggest, for a start, to have some kind of feeling of how many tests do you need. There is generally, I mean, it's a trade-off of how much time you spend on writing tests and how much time you gain by not debugging your code endlessly. And I would suggest, for start, to write at least 2 unit tests for every function. So every function should have a normal path, so what you expect it to do. So say, if I have a function that has to sum 2 positive integers, for instance. So it needs to, like, one of the tests would be to just throw a bunch of random integers into it and expect the correct results from it. Something like that. Another test case would be to test for extreme cases. So if I test some vector, for instance, try to pass like last element, first element, and so on. So the things that can actually break, that are on the boundary of what is allowed in your function. It's hard to tell you a good example without looking at the code, but I guess when looking at like homeworks and so on, you will kind of get that feeling. I want to stress it, make writing unit tests a habit. Like, it might be, like, some people are against it. There is like a bunch of people who say, hey, we don't need tests at all. But I believe that the majority of developers, of professional developers in the world, they write tests, and they believe that writing tests is important. And if you make it as a habit, it will make your life less painful when something goes wrong, because you will at least know what you can trust and what you cannot. So how do the tests look? It's basically, they're defined still in a CPP file within the testing framework, and you basically define so a dummy test file would be something like this. You have this test word, the keyword. You can think of it as a function. It's actually, it's a macro, but it doesn't really matter. But what it does, it generates a lot of code for you. What you need to write is just this. You just type test. This is the name of the module that you test. It can be anything, like you can write test blah blah, but it has to be something meaningful usually, because you want to understand what are you testing here. And then you give some function name. It doesn't have to be exactly the function name that you're testing over here. It can be a bit different, but again, it's just for disambiguating different tests. So one test will have the function name, the other will have function name too, and so on. They can also have like test function name for zeros or something, or test function name for ones or something. So it can be any name, but the main idea is that these names have to be unique. So the combination of these 2 guys has to be unique in all your tests. And there can be as many of those tests as you want it to be. So you can define many of those in the same file, and they can also be pretty big. So it doesn't just have to have this expect equals. It can be, you can create your object or create your variables, do something with them, and then check the results of your operations. I think we will also go into some examples a bit later. So the successful output of a test looks something like this. So when you run your tests, you will get this particular pattern of things. So if it's passed, like if all the tests that you've run passed, you will get the passed in the end. And every test will have a run and OK. So run is the start of the test, OK is the positive end of the test. So if it didn't fail, you will see this. If it fails, you will see the error with which it fails. So usually you expect some value over there, but it's not the value that you actually expect, and that's why it will fail. Good. So how do we add them with CMake? That's why I started the whole thing with CMake, so that we are not scared when we see something like add subdirectory. And add subdirectory is just the same, so it just happens to have a name tests here, but it can be any name whatsoever. The important part is the contents of this. Usually it's tests. And for the length of this course, I urge you to use tests as your testing folder. I will expect that there is a tests folder in your code, because that's from now on the way your code will be checked. So I will basically inject my own tests into your project and will run your code against my tests, right? And that is what you will get in the output of your homework. So this is important. You will use it every time. You need to specify, to enable testing, you need to tell it to CMake. And the good part with CMake is it just texts. So you just tell it, hey, enable testing. And he goes like, yeah, okay, I will do it. That's it. So that's what you add to it. And if you, so in all of the virtual machines that I distributed to you, there is the libgtest.dev is already pre-installed. If you run your own system, you need to install this. If you're on a Mac, you probably can also install it from Brew or something like that. What it does, this thing is a bit different from a typical program that you install. So a typical program you install installs binaries of that program. Because of the way Google Test is distributed, this thing just copies the sources of the latest Google Test into your system folders, and you will still need to create a library from them, compile them, and so on. But we will come to that, I think on the next slide. All right, I guess we will spend some time on this slide because, again, like it's a bit bloated, but the cool part is that all the code you need for doing tests, this is a real file from a real project, and it fits on the screen of a presentation. Like, I think that shows that it's not very hard. And also it can be shortened, but I think in this way it's a bit even more readable. So let's start from the top. If you add, so what you need to do is, now you have Gtest or Google Test in your, on your system. It's actually in user source, so it's installed in your system files. And this is just a folder which contains the sources of your Google tests. And we can easily actually see it by going to user source. And if we go to Gtest, this is the folder, so it exists, and the contents of this folder are just these. So it's a CMake, it's a small CMake project over there, and don't look into the CMake file, Cmakelists.txt and so on of that project, because you might get scared, because it was done to work on any system, and it adds a lot of boilerplate. If you want to, you can look into it, of course, but it's not as simple as the ones in the course. And if you go to the source folder of this thing, you will get a bunch of CC, which is just the Google's way of calling CPP files. They just call them CC files. I think it's just a preference of a company or personal preference. But there are like some header files, there are some CC files, and these are the things that will be compiled, right? So it is a bit more difficult than what we did in the start of this lecture, but it's essentially the same thing, right? So it still does the same thing. It still adds subdirectory. It does exactly the same things over there. And what it does, the only difference here is that we don't pass just one path to it as we did before, but we pass two things. So the second thing is needed to know where we want to generate our build files, because if this folder is not in our project, then we need to pass another folder where the build files will be written to. And they will be written into the project binary directory, which is usually our build folder, and we'll put a gtest in the end. So that's where all the compiled Google library will land, okay? Then the next important line is include ctest. Ctest is another program. It's just like CMake, but called CTest. And this is the program that you generally run to run through all your tests. Must be kidding me. Okay, so so CTest works with CMake to run all your tests. Okay, that's all you need to know about CTest at this point. Then we set a variable that is just a useful variable in case we want to change something. And this variable is this test binary over here. We just set it to a value of this. We have some project name, and this project name, we just concatenate this part to the project name, and we set it to the test binary. Okay, so no magic over there. And we can also just omit it and just use the same thing over and over, but it's nice to define it once and then just use it as a variable, right? So whenever we use it as a variable, something like this, we just get that value over here. Good. And then, again, there is nothing new. It's just the same things as we did before, but the only difference is that in the libraries that we link to. So we do the add executable, we create a test binary from the test tool CPP, which is our file where we set our tests. And then we do the target link libraries of our test binary towards tools, which is a library that we are actually testing. And these are the libraries from Google Test. They will always be there. So these things will always be there. This you will need to change whenever you define your own library that you want to check. And the only new thing here is that you need to add test. So add test means that you communicate to CTest and say, hey, this binary is actually a test command. So whenever I ask you to run my tests, please run it. Like that's what it says. And it says that, okay, well, the name is going to be test binary, and the command is going to be this. So it's going to be searched in the executable output path that we set somewhere, and it will be a test binary over here. This thing is completely compatible with the previous lecture. So if you create a CMake project, just kind of copy-pasting code from the previous lecture, and then add this on top of it, it should work. Right, so how do we run the tests? Now that we know how to configure the tests, we want to also run them, because that was the initial idea. And the cool part of it is that it doesn't change our process at all. Like, we just do the same things. We go to the project folder, we do the build, we do the make, we do the CMake, we do the make, and then we do one more step. We do the CTest minus VV. So VV is very verbose, basically. So you want to see everything. If you don't do it, it will just tell you if the tests have passed or not. But if you pass the VV, it will also show you the output of every single test. And that's generally what you want to have. So that's basically it. That's all you need to know to write your tests. And yeah, so we can also do an example of that again live, if you want to, if that helps. I'm not sure, like, does it help you when we do it like this, or does it just make you more confused? Do you, like, who wants to see it live? Okay. It's like half. Okay. Okay, let's do it. Let's just add things to our project that we already created. Okay, I need to go to temp, CMake project. So we are back in our project that we had before. Sorry. So this is our project that we started off this lecture from, right? So now let's just create the tests folder. So we created the test folder at this point, and let's also do the add subdirectory. Add subdirectory. Okay, and so again, like, the thing will work regardless of if I pass this thing over here. I can just use tests there. So let's actually probably do it this way so that we're sure that everything works. Good. Now that we added this subdirectory, we want to also create a cmakelists.txt in the test, because otherwise we will get an error just like we did before, right? So now that, okay, so what we need to do is we need to add a subdirectory, user source gtest, and let's project binary directory gtest include. Okay, so at this point we have, at this point it will compile the Google test library and it will include the C-test. So let's probably just stop at that. And before test, it's very important, we need to enable testing. The only kind of thing that annoys me with this, that is not logical, that I never can remember, is that you need to call enable testing from the topmost CMake. You cannot do it from the tests folder. So you must do it in the topmost CMake. So yeah, kind of Cmakelists. Okay. This is like, you just need to remember that. I don't know why it's that way, but so be aware of that. Okay, so at this point we have an empty testing suite. So we can do the CMake, and we can do a make. This make will take a bit longer than before, because now it does the same thing as it did for our libraries, but it does it for gtest. So it scans dependencies of gtest, build in CXX object, blah, 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 and then link in a static library libgtest.a. Then it does the same thing for gtest main. And there are two files. There is gtest and gtest main. Gtest main is just the main function for Google test. That's it. Like, it doesn't have anything else to it. So that's because they want to give you all the code. They don't want just to give you a library. They want to give you a library and a main function to run this library. Good. So now we have that. And also, you can see that another point that I made last time, but now I think it's even better seen, is that we do not rebuild our hello, blah, and bin main, because they were already built. We do not touch them this time, so we do not need to build them again. So make is smart enough to find out, hey, we didn't change them, so we don't need to touch them at all. So that's what is going on here. Good. Now, now we want to actually test our library, right? So let's try to test our blah library. It's a very useful name. For that, we go to tests, and let's just create a test blah.cpp file. Right? So in this test blah.cpp file, we need to include gtest gtest.h, I think, if I'm not mistaken. That is basically just tells you that you want to use Google tests. And then we want to include the blah.h, and then we can write a test. So we want to test blah, output test, whatever. Good. So now we have some empty function over here, and let's do a dummy test over here. Expect equals 1, 1. Right? So it's very stupid. Like, we just want to check that 1 is equals to 1. What do we have to do here is, if we try to build it now, we will not get an error. Why did we not get an error? Ah, yeah, right, because we didn't add test blah to the CMake. So we want to edit our CMake in CMake lists file in the tests folder. because now we have a new testing executable, and we want to add that executable. So we add an executable test blah, and right, test blah, and we also need to specify that it's a CPP, there is a test blah CPP file. Then we want to target link libraries, our test blah to gtest and gtest main. And if we do that, we still get an error, I believe. Oops. No, we don't. Why? Can we run it? Does it? Okay, it did build the test blah. How does? This is strange. Okay, so let's see how our source blah.h looks like. Has a, yeah, because we never call this function. So if we would call this function, we would get an error, because otherwise, whatever we don't call doesn't have to be linked. So you don't pay for what you're not using. And let's change our blah to actually to have a sum function again, and then let's have a int a, int b, and let's go to blah.cpp, and in blah.cpp now it's going to be a sum, int a, int b, and it will just return a plus b. Okay. And it should be not a void function, it should be an integer function. Good, so now we have this sum thing, and so the semantics of this expect equals is first you give a value that you expect, then you give a value that that you give to it, right? So like that you are testing. And for now, we expect that the sum of 1 and 1 is going to be 1. And of course, it's wrong. So let's try to build that. And now it should fail. I'm confident 99%. Cool, it fails. Because why? Now the main fails. Because the main still uses the old one. Sorry that it gets a bit confusing. The problem is that our old main function still uses the print blah, so we just remove it from here to make sure that we don't have that issue. Okay, now it fails with the error that I expected to fail with. Like now you have this linker error, ld returned 1, and the problem is that there is an undefined reference to sum. And that is because we never linked our library to the actual test that we are running. So we want to add the blah library over here. And let's also do the add test. Test blah. Test blah. Okay, let's try to make this one. No. Okay, cool. So now it did build. And if you look at our build folder, with the contents of our build folder, we now have the folder gtest. The gtest folder is where our Google tests have been built, the build files for the Google testing library. We also have the folder tests over here, and this folder tests contains our new executable. So if we just run something from tests, there is a test blah executable over there, so we can run it, and you can see that there is a bunch of things happening over here, and it has failed, right? So when it fails, it gives us some helpful output. Like it gives us this that the sum of 1 and 1 is actual 2, but expected 1. And this is what you want. So that's how you do it. Like you have a small function, you write a bunch of tests for a small function, you test every small public, like every small function that you can get access to, and then you're sure that this function works as expected. Okay, so I hope this is clear, because we don't really have much more time on it now. But again, if something is not, come to me and we will discuss that. I want to talk about namespaces a little bit. So we have actually seen them already. Whenever you use like cout, cr, and del, you're using a namespace. You're using the std namespace. You're using this std double dot something. But you don't, like, it's just because those functions are defined in a namespace, you can also define your own namespaces. So for instance, there can be module 1 and module 2, and they can have different namespaces. So like namespace like this and namespace like this, and why people do it is because people don't want to create different names of functions. So if I have a function print in my namespace, I don't want it to clash with other print functions in somebody else's library, and therefore, and I don't want to name it differently. I don't want to name it print, my beautiful print, I don't know, something like that. Because it gets annoying, it doesn't explain what the function is doing. You still want to call it the way it is, but you can put it in your own namespace. And this way, namespace becomes part of the type signature of your function. And this way, it doesn't clash with other function that is called the same name. So it kind of like, it can look like this. We can have two functions, the getMeaningOfLife function, and there is a fun namespace and a boring namespace. And you can use both of them if you want to. So we can call the boring namespace and we can use the fun namespace in the same situation. And this will compile perfectly well because these functions are different, even though they have the same name. But because they are in a different namespace, they are actually different functions. All right. We were using namespace std before, and sometimes it's still fine to use it, but never ever use that in header file, because it means that everybody who includes your header file will be using namespace std, which means that every function from std namespace will now be populating your environment, and you will be able to call it without the std prefix. So if I want to define my own function cout, for instance, or my own vector, for instance, then I will not be able to do it because now suddenly its name will not be std vector, but it's going to be just vector. All right? So try to not use it, and we will come to the situation to what can we do better with it. So in this small example, if we want to define power function to put something into power, and we define it, it just happens so that we define it in just the same way as it is defined in the math library in the standard library of C++. And the problem is that we were using this using namespace std, so now we have a function power from the standard library, and we don't need to use std to call that. And now it clashes with our library because we don't have a namespace for our library too. And we will have a problem here. So the output of this thing will be the call of overloaded power is ambiguous because the compiler does not know which function do we actually want to use. Do we want to use the one from the standard library, or do we want to use our own? Because their signature is exactly the same. Okay? I hope that makes sense. Generally, a good idea is to use only what we need. So don't use the world, use something that we are actually using. If we are using cout and del, just replace your using namespace std with using whatever you are actually using. If you are using cout in this file, say, I'm using cout in this file. And that will solve this particular issue because now power will have, like the standard power will be std pow, and our function will be just power. So now there is no issue, and now the compiler knows that we want to actually use our own handwritten power function. Good. So wrap up, like use namespaces in your code. So whenever you create a project, create it in a namespace. In the homework, you will have a namespace given to you in the header file. You will have to use it throughout your code. And I think it's generally a really good practice whenever you define your own library, wrap everything in a namespace. You usually want a short namespace because it creates a very long name if you have a long namespace name. The namespaces can also be nested. So you can have a namespace in a namespace in a namespace. And I will not explain it here now, but you can easily try it out. So this is not too hard. Good. Also, it's a good style idea to always, when you create a namespace, end it with this. So put a comment with namespace and then the name of your namespace. This way you will know where each of the namespaces end. It will come handy when you have nested namespaces. Okay, so the good way of using things is to call using my namespace some function, or just use explicitly the function with the namespace. So the way we do it usually is calling like std cout instead of using std cout and then just calling cout. Never use using namespace something in header file because it populates it to anybody who relies on your header file. Also try to avoid using this using directive in the header file too. Like it's not as bad as the using namespace thing, but it's still kind of bad. Okay, and just prefer using the explicit using, so kind of this using, even in the CPP files. Even though you can use using namespace in the CPP files because nobody will include them, it's still a better idea to not include the world if you are not actually using much of it. Good. So that was a short thing about namespaces. I think that was an appropriate time to do them. One more thing about that is you can have nameless namespaces. So if you write your CPP file and you find yourself that you are using some number, don't ever use just a bare number in your code. Like if you want to say like your local variable will always be 10, don't ever write it in a function like I equals 10 or something, because it's called a hard-coded value, and these are really bad. So this is like the first, if you look at the code and it's populated with hard-coded values, it's a first indicator that this code is not written well. Don't ever do that. If you need some constant that you will always be using, and it should be local to your CPP file, create a nameless namespace in the top of the CPP file and put it there. So it looks something like this. You can have a namespace, it doesn't have a name, and you have some integer, some float. It can be any possible thing that you might want to use. The reason to do that is that because these variables will only be available in this CPP file within this small module. They will not be propagated to anybody else, so you will not populate anybody else's code with your variables that don't need to be there. And you will also have a kind of a short list of everything that you are using on the top of your file instead of hidden somewhere in your code. All right? Good. So now is a very, very important topic. We start with classes. Classes make us create new types. Because before we were working with like integer, float, and string and so on. And actually string and vector are not fundamental types. They're not defined in the language. They are provided by a library. They are just a class. And this is what we will learn now. Okay, so the idea of the classes is really, really, really important. So if you did Java, you know what classes are. And you probably know that in Java you cannot write anything not in a class, right? In C++ you can. Sometimes you have to. So C++ is not an object-oriented language. It's a multi-paradigm language. You can use any paradigm that you want, and one of them is object-oriented programming. But the idea of the classes is that they encapsulate the data. That is why they were created. It's like one of the main reasons of them. And what do I mean by encapsulate the data? It means that there is some data that is stored in the class, and the only methods that I need to manipulate this data are also within this class. So it never happens that I store something in a class and I process it with some other function in some other file. And this is very nice to read in the code, because if you open a file, you know that whatever you store within this class will be manipulated exclusively from within this file. And this is nice because you can get, if something is wrong with my class that I've written, I know where to look for the error. It's always in this one file, right? And this makes life so much better and easier. Good. So there are two keywords for creating classes in C++. They're class, of creating types. They're class and struct. And the words type and class will be used interchangeably. So they mean exactly the same thing in C++. Apart from, okay, not exactly the same thing. Very close to exactly the same thing. There are fundamental types that come with the language, and then anything else is a class. So any other type is a class. Whenever you create a new class, you create a new type. Whenever you create an object of some type, it's an instance of a class. So we will use this terminology throughout this course. So I will use class and type interchangeably for classes, and I will use the instance of a class or object of a class for an object that is created as a variable of some type. Right. So the class looks something like this. Let's just dive into example first, and then we'll figure out what we see on the screen. So let's say we have a really simple image class, and there are a couple of things to see here. So first of all, every class starts with the word class. So you write class, then you type its name, then you open a bracket, and you have to close this bracket with the semicolon in the end. If you compile your code with warnings, it will actually tell you if you forgot the semicolon. If you don't compile your code with warnings, it usually works, but sometimes it doesn't, and then you will hate yourself. So enable warnings. Right, so there are public parts of the class and there are private parts of the class. What does it mean, public and private? Public is everybody can use it, so anybody can see it. Anybody who can have an object of your class, they can get access to anything that is under public. What is private? Private is anything that nobody has access to. So for instance, if I create an image, and I pass this thing over here, it goes right into here. And then what I can use on this image is the draw function, but I cannot call rows or columns. And to call things of an object, you use a dot. So if I have an object, I use a dot, and I can use a function from within a class. Good, so that was just like a small example to kind of get us started. And let's talk about the syntax of the class a bit in depth. I already told you that the definition starts with the word class. The classes can have 3 access modifiers. So the private, protected, and public. Private means that nobody ever, apart from this particular class, can have access to something. Protected means that, okay, we will, for now, ignore protected. We will come to that a bit later. Also, I guess the most important words here are private and public because they give you the concept. You want to protect access to something, and you want to allow access to something else, right? For the sake of this particular lecture here, protected will behave exactly the same as private. Public means that anybody can have access to it. By default, in the class, everything is private. If you do not specify any access modifier, everything will be private, and you will not be able to use this class. It's a good idea to start your class with public always, and then explicitly write private, because it makes an explicit interface, and usually people who read your code, when they read your, say, header file with a class, they will go from the top to bottom, and they will start with public, and the public interface is what they are usually interested in. That is what they care about. They care about how to use your class. They don't really care about the implementation of your class if this class works well. The classes can contain data and functions. So just like we saw here, it has some data, there are 2 integers, and it has a function draw, right? So that's fairly simple. The functions can manipulate the data. So any function that you call in your public interface can do whatever it wants to do with the private members of this class. Again, like you access any member by a dot. You could theoretically, if I would put this into public, I could also just access the integer value. I don't have to call the function all the time. But it's considered a really bad taste, so don't do it. It's possible to do it, but don't. The idea is that you always want to use a function to manipulate your data. There are 2 types of special functions, at least 2 types. We will talk about more of them later, but there are at least 2 types of special functions. They're the constructors and destructors. So the life of every object starts with calling a function called constructor. The life of every object ends with calling a destructor. Basically, that's it. And also name the classes in camel case, as Google style suggests. Right, so I also told you that there is another keyword, struct. Struct is actually a class, but everything is public. So struct can look something like this. You have some values over here, but you should never use functions in the struct unless you are doing some educational example and just showing some stuff, and you don't really want to do private members. So kind of in a tutorial to explain some concept, it's fine, but that's it. Like whenever you have a structure and you feel like you need to add a function to it, that should be a class. You can use structures still as simple data containers. So if you want to wrap a couple of things together that logically should be wrapped together, it should probably be a struct. And this way you can also return something from a function. So you know that functions return one value, right? But you can return a struct, which becomes as many values as you want it to be, because you can pack them into one structure, right? Okay, cool. So that's basically everything you need to know about the structures, apart from how to initialize them. The cool part about the structures is you can initialize them really, really nicely. You can use braced initialization, and if we have a structure called named int, let's say we want to name our integers, and we want to print some structure like this, we can actually now, we don't need to create a structure, then pass a const reference to it and so on. We don't need to do it. We can just do it like this. So it will be constructed in place, and generally the compiler will be smart enough to not even construct it in place, but just kind of inline everything and call it very efficiently. But the syntax is clear, right? So you just use the curly brackets, and you pass the values in exactly the same order as they are defined in the struct. If your order is wrong, your types will not match somewhere, and the compiler will complain. But that's basically it. So it makes syntax very nice. Also, you can use the same syntax for returning from functions. If you have a struct that you want to return from functions, you can create all its components and then just put the curly brackets and put all them in a row, and that's it. You don't ever need to write the type of the function, and it makes it really nice and readable. But then again, structures are really simple, and they're just the container of the data. The classes can store data of any type. So it can be a string, an integer, another class. It can be anything. If we follow Google style, and I strongly suggest you to, all the data should be private. That is kind of the core of encapsulation. Nobody should have access to your data. The only way people can have access to your data is through the functions that you give to them through your public interface. Because, so say if I have a car, and say my car is my class, right? I don't want people to be able to change the time of my clock from anywhere. I want them to call the public function of open door, enter the vehicle, and then press the buttons. So these are all public interfaces of the things that you need to do in order to manipulate some private data. I hope that example was a bit clear. It's kind of done on the spot. Maybe it wasn't the best one. But you can see the examples of this not in the code, but everywhere in life. Most of the objects that we interact with have a public interface that we interact to, and then we manipulate the private data. Our keyboard on the laptop is a public interface for us to communicate with, say, a compiler. We do not change the bits of our processor on our own because we cannot do that, because we have a public interface for that, right? So think about public interface as the only allowed way to manipulate the data that is stored in your class. There is an important difference to naming the members, the data members of your class. They're named just like any variable would be named, but they have a trailing underscore in the end. This is very useful when you are within a function of your class. You want to make sure, you want to know if you're working on a private member or not on a private member. And for that, you just kind of add this trailing underscore. The data should be set in the constructor, and if you have some data that needs explicit cleanup, then you do it in the destructor. For example, if you open a file for reading, like there is in the standard library, there is this fstream that it's just like cout, or like cin, but it works with files. So what it does is it opens the file in the constructor, and whenever it gets destructed, it closes the file. That way you can never forget to close the file. You can never forget to release your resources. And this is generally called resource allocation is initialization. It's a very important principle, better known as RAI. C++ community really is bad in abbreviations. Every abbreviation that you know that you see in C++ will make no sense at all. But it's a very important concept that you must remember, and it kind of governs the way to think about the code. So you need to make sure that whatever resource you acquire, it can be a file, it can be memory, it can be anything, is in the constructor on the moment when you create an object. And whenever you destroy your object, the resource will be automatically released. So you as a programmer, you don't want to think. You want to be lazy, and you want to just do like code stuff in the way that you don't have to remember doing stuff, right? Ideally, I would like to not write any code at all, and everything would just happen magically, right? That's my goal. So I want to write as few code as I can to make everything work reliably, right? The moment I need to remember something, I will fail, because my memory is really, really bad. And I will make mistakes. I don't like that. So that's why you use that particular way, and it allows you to not think about what you're doing. You know what you've done, and it will always happen in the same way. So this is a very important concept. Right, so I basically already told most of the things that you need to remember about constructors and destructors, but now let's talk about the syntax and what is required by the C++ language from you. So every class has to have at least one constructor. If you don't specify a constructor, so again, like a constructor is it's just a so a constructor is something like this. So if you have an image class, there is a function that doesn't have a return type, and it can take any number of input parameters, and it's called exactly in the same way as the class, and that is your constructor. So they're always named as the class. And if you don't specify an explicit constructor, a default one with no parameters will be generated for you by default. So C++ will say, okay, well, nobody defined a constructor. I will just do a simple one that doesn't initialize anything. It just creates an object, and that's it. Everything stays in the state where it's uninitialized. A destructor for, say, a class called SomeClass it's very similar to a constructor, but it never takes any parameters, and it starts with a tilde. So you always started with a tilde, and that is a destructor. And your class can have exactly one destructor. It must have one destructor, and the maximum number of destructors it can have is 1. And you can, if you don't add one yourself, one will be generated for you automatically. And usually that's what you want. You don't want to write your own destructors for many types. I think in this course we won't ever need to write our own destructor unless for educational purposes that we can write one. But the modern way of dealing with C++ is you should avoid writing explicit destructors as much as possible. So there are many ways to create instance of an object. Like let's do some example over here. So we have some class, it has a constructor, this is called a default constructor. There are some custom constructors that take 1 parameter or 2 parameters, and there is a destructor. It's just for educational purposes. You generally don't need a destructor, but you might need some of the constructors. So what you can do here is you can create a default constructed value. So the C++ will know which one to call, just in the same way it knows how to call a function. When you call something, it will know exactly in the same way which constructor to call. And there are other ways. So you can just use the typical brackets, and it will find out that it has to use that constructor over there. But in C++11, you can use curly brackets everywhere. And I suggest you strongly to use curly brackets everywhere. So this thing is exactly equivalent to this thing. The only small difference that makes it a bit better is that if I pass here, say, .0, that becomes a double, and I need an integer, and the compiler will not compile this and will say, well, I cannot convert, like, you're trying to convert a double to an integer, and this won't fly. So let's just not do it. And please make sure that you're using the correct type when you're doing it. And it makes your code more readable and makes it nicer to avoid small mistakes that can cause errors. Also, you can use the initialization like this. You can say equals and then just a number of parameters in the brackets. It's just a personal preference. There is no better, no worse here. Use the one that you feel that you like more. Right, so the data. Let's talk about how can we manipulate the data. The best way is to set the data in the constructor. You should avoid having a function called set something, because it basically is the same as just exposing it to the world. Like anybody can just set it or get it, and that is usually not the best idea unless you're implementing something that mimics like a functionality of a vector or something, right? So if a vector, you might want to give access to a particular element, or in an image you might want to give access to a particular pixel, and you don't explicitly want to know that somebody changed this pixel because you don't care. But generally, you want to avoid setters. If we avoid setters, how do we set the data? Well, we do it in the constructor. And the best way is to use the initializer list. Now, the initializer list is this construction over here. You use this colon over here, and then you basically initialize every variable of those with a value that you pass in the constructor. Just learn the syntax. The syntax is very useful, and also you have an empty function after that. So this is the definition of the constructor. It's not a declaration, it's a definition at this point. You can return data with getters. Like, so if your class has a property, and so say I have an ID and I have a name, and I want to be able to query the ID and name, but I don't want to allow people change my ID or name. This way I can create the getters. And the getters have a different naming scheme. They're not, even though they're functions, you can name them exactly as the variable that they actually return, just without the trailing underscore. So for instance, for ID, I would have the small ID, and for name, I would have a small name over here. And a very standard pattern that you see is for big classes like string or something, like not fundamental types, you want to return a const reference to a thing. So in this situation, we return a const reference. This way, we do not copy the string to somebody else, but we give them a constant reference. So they still cannot change it, but we don't pay for copying it. So this way, this return name will not return the string, but it will return a constant reference to our name. And this is usually completely enough for whoever wants to get our name. If they just want to print it, they don't really need to have their own object of our name. They just need to have access to our object. And this way we give them constant access to our object. Now we come to const correctness, and const correctness becomes kind of even harder than it was in functions. So if you have issues with functions and using const there, it's going to be a bit worse here at the start, but then when you get used to using things correctly, it will protect you from a lot of errors that you might do. You can mark a function as const when you're using it. So for example, you can see const over here after the name. So const after the name means that this function will never change the object. It cannot change the object. At this point, whenever you use this const, whatever you do here considers all these variables as constant. Does that make sense? So whenever you pass this const after a function, you cannot change anything within the object. It's perfect for getters and so on. Generally, prefer to mark const every function that you don't expect to change the state of your object. It doesn't matter if you need it because of C++, but just think about it. Like, does it make sense that this function should change an object? If it makes sense that it should change an object, don't use const. But if there is no reason why it should change the object, use const. So say something like print should never change an object or something like that, okay? And the cool part about it is that if we use this correctly, then by compiling our code, we know that there is no mistake. We know that we're not doing something that we don't expect to do. So it's kind of a contract between us and the program, and it's very, 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 very helpful. I can't stress it enough. The typical const error can look something like this. So let's say we have a function print, and we give it a student. So we want to print the name of the student. And we give it by const reference. The problem here comes because we call a name here, but name is not marked as const, so it's not there. And the problem with that is that now the function cannot. This function does not guarantee that the object will stay the same. And that causes a problem because we are given a const reference. So we must guarantee that the object will not be changed. And we cannot guarantee it because our function theoretically can change an object, right? And the typical error that you can see is this. Passing const something as this argument discards qualifiers. So this discards qualifiers. There are two words that are an indicator of an error with const. Whenever you see them, it means you definitely have a problem with const, right? So just remember those two words. Right, you can do, everything else is kind of the same as with functions. You can still declare classes and you can define them. And you can do it in header files and in CPP files. And you're doing it just the same, apart from one small difference. Whenever you define a function, you need to pass its name before the name of the class before the function. And you can do it for any function, like classes, like the constructors, destructors, or any other function that you might want. But that's the whole difference. I think I have like 1 or 2 slides more. We're nearly done, but there are some important points here. So try to, you can, in C++11, you can initialize the members of the class in place. So if I create a class, I know a default value for it. It's a good default value, and it always should be like that. I want to have a class student, and you have earned points, and you have happiness. And I want like to initialize your earned points to 0 and your happiness to be in 1, for instance, right? That's what I expect my class to do whenever I construct an object with a default constructor. So now whenever I construct it with a default constructor, I don't get uninitialized values, I get values that I know what they should contain, right? And this is a really nice thing. The only pitfall here is you cannot do it with structs. If you do it with structs, you lose the ability of passing them by curly brackets. So don't use it in structs. Anyway, in structs, you should always initialize everything, and you should only use structs only with the initializer list, like with the brackets. So you can use classes as modules. So every class should encapsulate its data and the methods to work on this data. And usually the way they're separated is you put some class in a header file and you have some class.cpp to implement that. It's just the same as with functions, but now you have a single class per file. So in your one header there is one class, in your one CPP there is a definition of this class. Okay, so we're done, a bit over time, but I hope some things were clear today. You can read about const correctness in the CPP, like one of the big C++ sites, and also you can read how to use the Google tests in depth if you want to at their page. I'm sorry I had to shorten the URL because it didn't fit on the slide. Okay, so thank you, and sorry for being a bit late. Yeah.